And we're back. We are going to be computing the volume using a method called the shell method. And we use the shell method when the disk or washer method it is a little awkward or inconvenient, or actually would be harder. Now the shell method consists, well, it happens when we have some function. So let's look at this one here. We have some function as indicated by the black line, and what we're going to do is we are going to rotate that function about the y-axis. And when we rotate it about the y-axis, so we're going to have this entire function, and that's just one of those shells. We're going to have this entire function rotating about that y-axis, and it'll be rotating from A to B, creating a hole in the center. So imagine that whole thing wrapped around, and what we're going to do is just create a bunch of little shells, as in this picture here. So if I take that shell and I unwrap it, notice that I could unwrap it. Its length here would be the circumference of that shell, which would be 2 pi, that's not a pi, times some distance, and we'll just call that distance this x distance, because that's going to be that length or that radius. The height of this shell is just going to be that function height. So if you'll notice what we're doing, we're taking these shells, there's 2 pi r, there's that circumference or the length of that shell all the way around, times the height, times however many shells there are, and we are going to try to create an infinite number of shells, so we're going to have the thickness of those shells. This is the thickness of that shell. We're going to have that number go to infinity. So here we have, that is the circumference of that shell, or the length of that shell, all the way around. That would be this distance here, and then the height of that shell times the thickness, and we're wanting that thickness to go to 0. So here it is, written out beautifully. And now let's try to work a problem with this. So what I did was I graphed this on my calculator. I graphed this x equals pi over 2, and this is what it would look like, if you were trying to graph it and trying to figure it out. We're going to revolve this thing about the y-axis. So I'm going to get rid of this piece, and I'm going to erase this piece and this piece here, because I want to be looking at and imagining this solid wrapped about the y-axis. So I'll erase that. So imagine, if you will, this solid piece right here revolved about the y-axis, creating this shell that goes all the way around. And I could look at that shell and this shell and imagine what that would look like. It would kind of look like a bowl that's filled at the sides and then has a flat bottom. So next what I do is I'm going to try to find the volume of this shell. So I know that it's going to be 2 pi, and I look at this x distance, and it goes from 0 to whatever that x value is, so that's just a plain x, and that makes it nice. Oops, I put my and I'm doing this from my limits of integration will be from 0 to this square root of pi over 2, square root pi over 2, and my function height, this one is just this function itself, which is sine of x squared, and then the x-axis. So you could say 0 if you want, or I'm not going to write that down. So you would say sine of x squared, and then you would say minus 0 if it didn't go down to that x-axis. Alright, so the next thing I need to do is I'm going to integrate this thing. Alright, just a short review of substitution method again. I'm just rearranging. I chose my u to be that inside function, which is just x squared. I did my du, and then I solve for x dx because I saw that I had both an x and a dx here. So just rearranging, bringing my constants out front, I'm going to do my substitution and then integrate. Alright, I've substituted here. I replaced that because this is in terms of x. I went ahead and said, well, u is x squared, so I squared whatever this number was. I didn't have to write 0 squared, but I was just trying to be doing this for clarity. And then I just did my substitutions. X dx is 1/2 du, and then this would be the sine of u. I'll finish up. Alright, finishing this one up, I just integrated and then put in my limits of integration and came up with that arithmetic and then got a pi. Alright, and this is just a visual that hopefully might look a little bit better, just gives a little 3D image of what I was trying to show up top here, where I was just rotating this entire thing about that y-axis. Alright, on to another one. And this would have been more difficult trying to use that disk method. It could be done though. Since I said that, I might as well tell you. So what I would do if I was going to use the disk method is I would probably say that I was going to rotate it about the y-axis and use a washer method this way, where this x equals square root of pi over 2 is my top function, and the bottom function would be that sine of x squared, and then I'd have to use my limits of integration being from this 0 on up to wherever it was it hit at this point, which I imagine would be 1. Visualizing these things is kind of the toughest part of this. I have the region bounded is just in the first quadrant, the line y equal 2 and y equal square root of x squared minus 2. So in that first quadrant, and there it is right there, I'm going to revolve this around the x-axis. So it's going to be revolved around this x-axis. If I'm to use the shell method, that means I'll be making shells where it will be integrated with respect to y. So I've got to imagine these shells as they go all the way around here and figure out exactly what's the circumference and what is the actual height here. So the volume is, you'll have to figure out your limits of integration. In this case it's fairly straightforward. We're integrating with respect to y, so this 0 to 2 would be my limits of integration. Next thing, I'm going to need the shell circumference. So the shell circumference, each shell has a circumference that's going to be 2 pi times whatever that, and the radius of each of those shells is whatever that height y is, so whatever that y value is. So there's going to be my shell circumference. Next, the height of each of these shells is just going to be this function value because it's revolved about the revolved about the x, and it just goes up to the y-axis. So that height is then going to be, I've got to rework this. Let's see, move that square root over at x minus 2. So it'll just be y squared plus 2. And then integrate with respect to y. So I'll do that integration for you. Alright, just here's my steps on the integration, and then I would just key in or punch in, plug in the 2, and then subtract off plugging in the 0. And that would be the volume of that solid as it's revolved around that x-axis. In our next example, we're going to take just some random sphere of radius capital R, and it is going to be drilled out with the hole little r. Okay, that's nice of them. We want to know what's the remaining volume, and so we're looking at this as if it is revolved about the y-axis. So let's really look at it. Revolved about this y-axis. Can you see this revolved about the y-axis so that I can get some idea of what my shells look like. Let me write down my formula. Alright, so let's look at my circumference first off. My circumference is right here. The circumference of this shell would be 2 pi, and it is always going to be whatever that distance x is there. So 2 pi x would be my circumference. You can look at the height in two different ways. You could look at it as just looking at the top of the ball and saying, well, it's just two of these, the volume of it's just going to be two of these f functions, or you could formally say it's f of x minus the g of x, and minus and minus makes it a plus, so it's still two of those r squared minus x squared quantities dx. And now my limits of integration are going to be from r, this capital R, to this little r. So alright, I'm not really going to want to integrate this as it is, so I'm going to let u equal the square root of r. Oops, I don't want the square root, I just want the r squared. Sorry about that. I want the inside function. So I just want the r squared minus x squared. Yep, there's what I want. And so then du is then going to equal negative 2x dx. Oh, I see that I have a 2 and an x and a dx. That makes me somewhat happy there. And then my limits of integration, I'm going to have to replace my x in this case. Instead of this x being here, I see that my x will be r squared. So it's going to look like, if I replace this right here with r squared minus r squared is 0. If I replace my x with this r, then I'll have r squared minus little r squared as my limits of integration. 2 pi, and then I guess I should have combined constants, but 2 square root u, and then this x dx then becomes, let's see, x dx, so then would become negative 1/2 du. Alright, so I'm going to piddle algebraically with that for just a minute. Alright, moving some things around, this is what I'll get. And then I'm going to integrate this u to the 1/2. I'm going to end up with, that's going to be 3/2. So I'll have to fix it with a 2/3, putting in my constants, negative 2 times pi. My limits of integration, 0 to r squared minus r squared. I'll finish that up. Alright, there's what it looks like. It's very beautiful. And of special note, if it didn't have a hole and this r was 0, that's what that would mean. So if r equal 0, what you would end up with is volume equals 4 pi over 3. And notice if that was 0, I would just then get r cubed. Oh, that little stinker. There's the volume of a sphere, and we just derived it. Okay, we're going to take this same region and we're going to do two different things with it. So let's look at our shapes that we're going to make. This one has me taking this region, and then we're going to revolve it about the line x equals negative 1/2. So this region is then just going to be revolved about this axis. Now, a little bit trickier. So let's look at what our limits of integration are going to be. Our limits of integration, we're going to look at this thing. Well, we already have our points listed from 0 to 1. I need that cylinder's radius. So that cylinder's radius is going to be whatever my x value happens to be at the time plus that 1/2. So here's going to be that radius there, which is just the x plus 1/2. So I've got 2 pi, not just a plain old x in this case, but an x plus a 1/2, because I'm not revolving it about the y-axis. That's a lot easier when you're revolving it about the y-axis, but this isn't. And then I need to figure out the height of this thing. So my height is always 1, but then it's kind of got a hole cut out of it at the bottom, and it's got this whole part cut out when it changes, and it's the 1 minus whatever this function is. So I would write that as 1 minus that square root of x dx. And now I'm going to do my little algebra so I can integrate. Alright, I just multiplied this out so that I could integrate each individual piece. Alright, when I do that and plug in my numbers for my limits of integration, I get 8 pi over 15 for the volume. In this next one, we're supposed to use the disk or washer method to find the volume of solid when it's revolved about that y equal 1. So I'm taking this region, revolving it about y equal 1, and I'm going to use the disk method. So I'm going to have these little disks, and these little disks are going to be revolved, and they'll kind of look like this, and they're going to make a solid as it revolves about that y equal 1. So the disk method, the formula for that was limits of integration, and it would just be pi r squared, and seeing as I'm revolving it about this y equal 1, I would integrate with respect to x. So what I get is, integrating with respect to x, that would be from 0 to 1. Pi. The radius of this is going to be this, basically it's the 1, because it has this whole chunk minus this empty spot, so it's really a 1 minus the square root of x quantity squared, because this is the part that makes the whole, so I have to subtract that part out, dx, and then I'll just do the integration. Alright, working through this integral, I get that the volume of this solid would be pi over 6. Next up, we have just a summary of the disk, washer, and shell methods, and when you're integrating with respect to x or to y axis, and just a summary of those. We've been through those examples, so I would keep this with you whenever you were going to take a test, so that you would have just a nice little summary that's in a beautiful little table, and I've got it in your instructor notes for you. Okay, I just get to figure out whichever method that I think would be most appropriate. I have this function bounded by these two regions, and I get to use the washer, and then I get to use the shell. Okay, I have to do two separate ones. Okay, so I'll do that. So here I go. I have to read the problem sometimes. I've got this little section here, and I'm going to rotate it about this just plain old x-axis. Good. So the first up, I see myself making these washers, so I'm going to do that one first. And for my washers, I have the formula v equals my limits of integration, and then it's pi. It's really just an extension of the disk method with a hole in it, so it's f of x squared minus g of x, and each of those squared. I guess it really is ugly there. Okay, and then with respect to x. So that's what I'm going to do. V equals my limits of integration. This is, I'm integrating this with respect to x, so I go back and forth across here, and I see that it goes from 0 to 1. Pi. and I need to find my top function. That is that's kind of ugly, 2x minus x squared, quantity squared, minus this whole, well, that one's not too bad, which is just x quantity squared dx, and I'll do that integration. Alright, so to do the shell method and create shells, that would look like this. I would have these little segments that would then revolve about this x-axis, so that I would have these shells of a particular height, kind of like this as they go around there. And I will need to get my formula, which is volume equals limits of integration, and then that is 2 pi. I'm going to have to integrate this one with respect to y, so it's 2 pi y, because my radius here on this is always going to be whatever that y value is. Here he is right here. There's whatever that y value is, whether you're on this shell up here or this one down here, that radius is always that y value. And then I've got to look at the outside and the inside function and figure out what's going to go on with that. And I'll need to rework that in terms of y. So let's look at what we've got on our, there's going to be my top function there. That one's pretty easy because that one is just y equals x. So that's my top function, and then I've got to figure out that bottom function on those heights, because it's going to be varying heights as it goes all along. Y minus, and then here's going to be the bottom of that thing as you make those shells. So I've got to say y equals 2x minus x squared. Alright, so well, this one certainly is messy. I had to rewrite that because I'm going to have to complete the square here in order to solve for x. So you'll end up with, in completing the square, you'll end up with some 1 minus y equals x minus 1 quantity squared, and then you'll take the square root of both sides, remembering that you have a plus minus case on that square root. And for our particular case, we're going to have 1 minus the square root of 1 minus y for our particular function. What a mess. Then I'm going to plug that in here, which is 1 minus square root of 1 minus y dy. And that is not really all that stunning. And to put my limits of integration on there, that'll be a 0 to 1. So I'm going to write down some of what I have here and do some algebra of this. So I'm still trying to set this up, and I'm looking at this one going, the integration here is going to be a mess. So the point of this particular problem was, I don't want to do this one by the shell method. I'm going to use, oh, I don't know what happened here. I'm going to use the disk method or the washer method here, because that one is much more straightforward. So you just have to look at your problems. If you're working on one and what you're doing happens to end up in some big old whopping mess like this one, go, maybe I should try a different method. And some of them are not solvable by all methods. So try something else if it doesn't work. And I'll see you at the